So the talk today is on Prony's problem and spectral theory, and it's based on a couple of papers that I wrote, one with Akram Al-Drubi around 2016, and the other one with Götz Funder that was submitted at the end of last year. And of course, thanks to NSF for sponsoring some of the work. Here is a little bit of the outline of the talk. So I'll start with three different identification problems that serve as the motivation for the type of research that we've been doing. One of them is the sparse identification of sparse vectors from consecutive Fourier coefficients. That's the original Prony's problem that dates back to at least like 1795. The other one is the system identification problem in dynamical sampling, which Akram and I got interested immediately once we started working on dynamical sampling around 2011. And the paper came out in 2016. That's one of the two papers that I mentioned. And the third problem was the one that Götz, among others, was interested in, and that's identifying linear combination of time-frequency shifts operators. So these are the three problems that on the surface of it look very different, but the goal of this talk is to show to you that there is indeed a lot of commonalities between the three. But to be able to grasp those commonalities, we need to go at a more abstract level. And for that, I would have to present some background for you, and that would be the background from the spectral theory of Banach modules. So once we have that background, that will be enough to formulate the abstract identification problem that indeed generalizes the three that I will show to you in the introduction. And we will see in the next part of the talk that Prony's method, the original Prony's method, generalizes essentially in the same way for the abstract problem. So the point of view will be completely different, but in the end, the algorithm itself will be very much the original Prony's algorithm, just viewed from a different perspective. And once we've discussed this method for the abstract problem, we'll come back to the original problems and see how it specializes down to some of those three problems. So that's my plan for today. And again, please feel free to ask questions at any time if I miss something in defining notation or definitions or anything else. All right, so let's start with the original Prony's problem. And that was to identify a sparse vector in d dimensions from 2s of its consecutive entries, right? So in the abstract, I switched the time and Fourier domains, right? I wrote that you can identify an S sparse vector from 2s of its consecutive Fourier coefficients. In this formulation of the problem, space and Fourier domains are switched, right? So I'm looking at a periodic function. I'm taking 2s of its consecutive values. And what I know is that I have only s, or at most s, non-zero Fourier coefficients, right? So it's the same problem, just replacing the time and the Fourier domain. And of course, there is an easy generalization of that if we go off grid. So now, rather than looking at a d-dimensional vector here, we can look at an almost periodic function of this form. And again, we want to have 2s of its equally spaced values, like x of 0, x of 1, x of 2, up to x of 2s minus 1. And we know that we have only s summons in this representation. So we want to identify this almost periodic function, which is typically called a super resolution problem, which was studied by many people. And as I said, the original original Prony's method goes back to 1795. This is the journal, a engineering journal that paper was published. The title of the paper is like 4 lines, so I decided not to give you the title. And Prony was, of course, more an engineer than a mathematician. And if you didn't know, his name is one of, I believe, 26 famous names that are etched on the Eiffel Tower in Paris. So we have a long connection there. Now, of course, since 1795, there were tons and tons of papers on generalization of Prony's method, numerics and everything. Just to give you 6 or 7 papers that were published within the last 4 years, here is a small list. All I did is yesterday or a few days before, I just decided to open MathSciNet and type in Prony. And of course, I got hundreds and hundreds of papers, and I picked some that are relatively recent. And I believe some of the people on that list are even here. I have to confess, I should have known this paper because this one is in spirit closer, probably the closest to what we'll be talking about here. But apparently, Gerland and her group and us were working more or less independently. We did talk to each other, and the work is, of course, different, but I should have read it before. So I'm sorry if there's too much, something that I haven't cited, basically. But anyway, so this is really a very, very small list of papers and that worked about Prony, that worked on generalizing Prony's method. And the work doesn't stop because of all the applications that it has, but also because all of the problems with numerical instability that the Prony's method usually has. So there's always a lot of work on how to make this method more numerically stable, more applicable. And I have to say, this is not something that we'll be talking about here, right? So the talk today is not about making the method more stable, or at least not really about it, but it's mostly a different general point of view on the method on what we're actually doing. Okay, so that was Prony's problem. Here is the system identification and dynamical sampling problem that Akram and I got interested in. And some of you, well, probably most of you do know, but for those of you who don't, dynamical sampling is a framework that Akram and I started to develop with Akram's then student, Jackie Davis, around 2011. And we wanted to use the techniques of sampling theory for signals that evolve in time. So basically, the original premise was to try to compensate insufficient sampling density in space with sampling in time, provided that we know that the function, the signal that we're sampling, evolves under an action of a linear operator. And the second problem in this framework, which we almost immediately got interested in, was what happens if we don't know which operator the signal involves, drives the system, right? So basically, the question is stated here. We want to determine at least the spectrum of an unknown operator matrix from its dynamical samples, right? So we have an unknown vector x. We apply an unknown linear operator to it, capital L times, and then measure the result against a certain subset of basic vectors. So we don't even observe the whole thing, we observe part of it. Right? We do know the set omega, but we don't know x, we don't know a, and we want to know the spectrum of a, right? So this was the system identification and dynamical sampling problem that Akram and I worked on about 10 years ago. And then after our paper, Akram's then student, Sui Tang, extended those results and looked at this problem in the infinite dimensional setting, and also in this paper with her colleague as well. So that's the second problem, system identification in dynamical sampling. And the third problem is what I called here the channel identification problem. It concerns with time frequency shift operators. That's probably most familiar to all of you here, right? So the time frequency operators pi lambda are simply compositions of translations and modulations. So they act on a function u via this standard formula, right? And then lambda is the index in R2. And these operators, as they realized 20-some years ago or more, are good to use, for example, to model time-variant channels, right? Once they started doing mobile communications, that's what they realized they could model the channels with. And then now you'd want to identify the time-variant channel through the measurements of some test transmissions, which in this language simply means that you have an unknown finite linear combination of time frequency shifts. You apply it to a test signal, and you somehow measure the results at the receiving end, and you want to figure out what that finite linear combination of time frequency shifts is. So this is the type of problem that Gertz and David were interested about 20 years ago, and also Charlie and his colleague wrote a paper on that in 2014, and that's just a sample of 2 papers. There are many more on that subject. All right, so I showed you 3 problems: Prony's method, identifying the spectrum of an operator, identifying the finite linear combination of time frequency shifts, and they are, in a way, a spectral identification problem, all of them. But is there a framework that will fit all of them in one go? And that's what this talk really about, to show you that abstract framework which encompasses all of those 3 problems. And already in our paper with Akram, which appeared in 2016, we adopted that point of view, which showed that the original Prony's problem is, in a way, a system identification problem in dynamical sampling. So this is what this slide hopefully will explain to you. And as I mentioned here, this is based on my paper with Akram. And around the same time, Peter and Blanca also had a very similar point of view on the same subject. It's slightly different, but there's a lot of similarities. So again, remember, the problem is, the Prony's problem is to identify the unknown S non-zero Fourier coefficients from the measurements of x of 0, x of 1, and so on. All right? So we can view it as measuring the translates at 0. All right? So what happens here is that the locations of the unknown non-zero Fourier coefficients could be determined by, could be denoted by f, right? And basically, we're looking for one almost periodic function with the unknown spectrum. And the key thing is that this translation operator leaves that space invariant. So if we look at all almost periodic functions with a fixed spectrum, then translation leaves this space alone, right? It's invariant for that space. In particular, it's invariant for the translation operator T1. And then it is not hard to see through some kind of a spectral mapping theorem result or something else that the spectrum of this restriction is precisely e to the 2 pi I gamma, where gamma is in the spectrum. So from that point of view, our measurements, Prony's measurements, are simply evaluating the nth power of the operator T1 at x, and then looking at the value at 0. And from these measurements, we want to identify the spectrum of the restriction of T1 to this module. So we want F, but knowing F is equivalent to knowing the spectrum. So in particular, Prony's problem is really identifying the spectrum of an unknown restriction of T1, which is a known linear operator. All right? T1 is a unitary representation, so the spectrum are the roots of unity. And the spectrum of the restriction are precisely those roots of unity which sit in the set F, which we want to identify. So this is the reduction of Prony's method to the system identification and dynamical sampling problem that Ackerman I tackled in that paper in 2016. But at this point, we're still quite far away from the channel identification problem. And to put that into the same framework, we need a lot more abstract theory. So please bear with me through the next several slides, where I'll try to give you some basics of that abstract theory, which will allow us to tie everything together. Any questions so far? All right, so we'll have to suffer through a little bit of notations and definitions. And G here will be a locally compact abelian group. If you don't want to worry about locally compact abelian group, think just RD or the torus or some power of the torus. That's going to be enough for this talk, but in principle, you can deal with any locally compact abelian group here. G hat is going to be its Pentragon dual. So the dual of RD is identified with RD itself. The dual of the torus is Z, and the integers, and the dual of the integers is back the torus, of course. And we will deal with Banach modules over a Berling algebra. And what is a Berling algebra? Well, it's an algebra of functions summable with weight W. And again, if you don't want to worry about the weight, just think L1, the group algebra L1, and in most cases that'll be enough. But for some of the examples that I'll show you here, we really do need the weighted algebra. But so this is again for the tools that we're using, the abstract theory is developed for Berling algebras as well. So as long as the weight is not too crazy, the theory is already there. Right, so as far as the abstract theory goes, we really just needed to take it off the shelf. We didn't need to develop more of the abstract theory for this talk. And just to remind you, the Banach module means that you have a bilinear map with the following properties. So this last property is what makes a module a Banach module. You have this inequality in norms. All right, and this G should be that G, my apologies. Okay, so we aren't really dealing with an arbitrary module structure. The module structure that we will consider will always be associated with some representation. And on the next page, I'll give you examples of typical representation. And then once you have it, the module structure will be given by this formula on the screen. And you should think of it as a convolution. Once we look at examples on the next page, we'll see that in the typical example that really is indeed a convolution. So that the spectrum in the spectral theory of the talk, the spectrum really that we're talking about is this Berling spectrum that we have here. it has this definition, which I won't bother to read for you. It's on the screen, but the way to think of it is something that generalizes both the support of the function and the support of its Fourier transform. Depending on the choice of the module structure, it could be either one. And it could also be many other things. So the next slide will give you a few examples so that you have something to keep in mind as we proceed. All right, so here are the friends that we've seen already. If you do the modulation, right, then we'll denote it by M. Here I chose to do it on the space of sequences, bounded sequences, L infinity of Z. I could do it on LP of the line, it doesn't matter. But in this case, the representation is this. So let's see if we write down the formula for the module structure, let's see what it becomes. All right, so according to the formula, Fx is the integral over the group f of t minus tx dt. All right, so for the case of the modulation, we're going to have the integral over the torus f of theta minus n d theta, which really just becomes, now where is my x? Sorry. Xn d theta, so that just becomes f hat of n x of n. All right, so this is simply multiplying by the Fourier transform. And if you look at the definition of the Berling spectrum, all right, so lambda does not belong to the Berling spectrum if there exists f in L1 or LW such that f hat of lambda is non-zero, but fx is 0. So if you look at the formula of the module structure, from here you can see immediately that the Berling spectrum is simply the support of the sequence. All right, so this would be precisely those x's where x of n is non-zero. And it's the same if we replace the space of sequences with LP, right? It'll be the support of the function. Now, if you do the translation, as in the second example, then the formula fx becomes simply the convolution, right? Because this is simply x of s minus t. And then the Berling spectrum becomes the support of the Fourier transform because this is 0 if and only if the Fourier transform is 0. And for the Fourier transform to be 0, the Fourier transform of the convolution is the product. So just like in the previous example, for this to be 0 with a non-zero f hat of n, x of n needs to be 0. Here, for this to be 0, if f hat is non-zero, x hat needs to be 0. All right, so that leads to this formula for the Berling spectrum. Of course, I'm cheating. This is all really understood in a sense of distributions if we're dealing with LP. In L2, yeah, so it's just the support in L2. So these are two most basic examples, but you could go to more exotic examples by looking, for example, at a set of matrices. So then your Banach space is bounded operators from little LP to LP, right? It's infinite matrices, in this case, bi-infinite matrices. And I stay away from the case of infinity because if you have some experience with infinite matrices, you can have a non-zero operator on little l infinity, which has a zero matrix, and that could create all sorts of troubles, which you want to stay away from. Okay, so now the representation is defined by this conjugation formula, where this m is still the modulation that we see right here. And then in this case, it turns out that the Burning spectrum precisely corresponds to the numbers of the non-zero diagonals of your matrix. So if the entire diagonal is zero, then that number is not in the Burning spectrum. If something on the diagonal is non-zero, then it is. All right. And then you can generalize these things. Instead of looking at scalar matrices, you can look at block matrices, and you do that by means of a resolution of the identity. So if you have a system of projections such that the series En x converges to x unconditionally for every x in the Banach space, then this is well defined. It is a representation. And then the Burning spectrum picks up all n's such that Enx is non-zero. All right, so Burning spectrum is a very good proxy for the notion of a support for elements of a Banach module. And it will probably not be much of a surprise for some of you that it's this spectrum that we will be identifying as part of the spectral identification problems that I'm talking about here. Any questions? All right, so a little bit more notation. Remember, we talked about the restrictions in the Prony problems, right? We want to have our known operator like the translation, and now we want to restrict it somewhere. So the restrictions, the spaces we want to restrict it are called spectral submodules, and they will consist of vectors in the Banach module which have the Burning spectrum in this set F. And this F and this F are the same F. Sorry for the typo in the font. Right, and especially interesting for our case are submodules where this set F is a singleton, and then this is the type of notation we will use. So for our problems, in reality, we'll have just F being a finite set, so the spectral submodule will be a finite union of this X subgamma. And it turns out that in many cases, the elements, the vectors that constitute those spectral submodules are eigenvectors of the representation, which means that this formula holds. So under certain conditions, all you have in those spectral submodules are vectors like this. Right? In other cases, you may have generalized eigenvectors, so it's a little bit more general than just this, but it's not a big deal for our theory. It's still covered by the framework that I'm trying to present to you. Right? And the name for the elements of X of F are, for that reason, are usually almost periodic vectors. So they're linear combinations of eigenvectors like this, just like the almost periodic functions in the classical sense. Now, if you want to know much more of those theories, there is a survey by my thesis advisor from 2006. This is mostly excerpts from his habilitation thesis of 20 years prior to that date, but with a little updates. And some of it is also in our joint paper that contains some of the results of my thesis, which was 2 years before that. Okay, so hopefully this is all we need with about the notation, and now I can formulate for you the abstract problem, which we found out covers the original spectral identification problems that I started the talk with. All right, so here's the abstract problem. We want to determine the Berling spectrum of an almost periodic vector in a Banach module from its measurements. All right, and I explained to you what Banach modules are. I explained to you what the Berling spectrum is. I explained to you what an almost periodic vector is. I haven't explained to you what measurements are. All right, so, but first, let me again write the formula for you. All right, so this is again the module, the product, the module structure. It's defined by this formula. And this is the signal model. All right, so I'm interested in identifying a vector x in a Banach module, which is a finite linear combination of generalized eigenvectors of my representation T. All right, so in this case, my f is unknown. The coefficients C gamma are unknown. What is known is the dimension m gamma. All right, so in simple cases, like in the original Prony's case, those spectral submodules that correspond to singletons are one-dimensional. In general, they don't have to be, so that's why it's generalized eigenvectors, and that's why we have the second sum here to account for generalized eigenvectors. But this is the thing that I want to identify, and it looks very much like the original Prony's problem, and indeed, Prony's problem is a special case of it, but the beauty is that the others are special cases as well. Okay, now if you want to see something more about almost periodicity, Radu and I wrote a paper about 15 years ago about an almost periodic non-commutative Wiener's lemma, so you can also find the definition of almost periodic vectors there. But the theory, more of the theory is back to this paper. All right, so again, the job is to design a Prony-type algorithm that identifies signals like this from their measurements. And the next key step for us is to figure out what those measurements are, which would also include the case of the original Prony's methods where we were simply evaluating the function x. Right, and these are the measurements that we're taking, and these are the type of measurements that Akram and I decided to take back in when we started doing dynamical sampling. All right, so we take our vector x, we apply powers of a fixed operator b to it, and then we take certain subsample of the measurements of the vector that we do, right? So we evaluate b to the Lx, v is certain functionals a. But so the rank of a should be finite dimensional because we want to actually be able to compute something in the end. And we shouldn't have infinitely many measurements. We shouldn't have to take infinitely many measurements because we only have finitely many unknowns, right? We have infinitely many possibilities for the set F, but it's a finite set. And m gamma is also a finite number, right? So we have finitely many degrees of freedom in our signal, which means that we should be able to recover it with finitely many measurements. Therefore, our operator A should have finite rank, and we shouldn't take more than finitely many powers of operators B, right? So how do we design those operators B? Well, B is something that should allow us to see the spectrum. And for that reason, we choose to take operator B as a linear combination of the representation. Right? So in particular, in the original case, that's simply T of 1. Right? The simplest linear combination you could possibly take, you take one place and you don't even have the sum, you just take T of 1. And then you take powers of T of 1, and your A is evaluation at 0. All right, so let me write it down. For Prony, again, V equals T of 1, the translation, and A of X is simply X of 0. Right? But in principle, you have a choice. You can, instead of T of 1, you can take a linear combination of different translates. And this G is, again, not this G. It should be this G. My apologies. And then instead of evaluating at 0, in principle, you can evaluate at several points. Maybe you will be evaluating the function and its derivative, and that in principle would give you hopefully better stability. So roughly speaking, the choice of B makes the recovery of the spectral set F possible. And the choice of A is governed by the fact that we need to have unique coefficients that give you the vector, so that you can you have only one possible answer once the spectra is determined. So these are the two different roles for the operators A and B. And B is there to recover F, A is there to recover the coefficients, roughly. They do play in concert, so it's not exactly like that. All right, so now we have the measurements, we have the signal. What is the method? Well, before we get to the method, here is the key theorem that tells us why the method is actually possible. Well, the signal, because the operator is like this, it leaves the spectral submodule invariant. Right? So we can denote by B sub F the restriction of the operator B to this spectral submodule. And there is a very general spectral mapping theorem, which you can find, for example, in that paper that I cited before, which says that the spectrum of this restriction is simply the range of this function h, which defines B, right? So B, in some sense, is a functional calculus of the generator of the representation, or generator of the module, whatever it is. We'll stay away from it. But this functional calculus connection is something that connects this point of view with the paper of with the latest paper of Gerland that I showed to you in the beginning of the talk. All right, so again, at this general situation, we see that finding F here really amounts to identifying the spectrum of an unknown restriction of a known linear operator. Right? So we have a choice of these BNs. So this operator is completely known to us. And because of the spectral theorem, we should know the spectrum of this operator on the whole space. Right? Our job is to be able to recover the spectrum of the restriction. So as I said in the abstract, Prony's problem from this point of view is really identifying the spectrum of an unknown restriction of a known linear operator. And it turns out that the method is the same. Right? So there are different ways of describing Prony's method in the literature. And this is one of them. Right? So for other methods, you'll have different ways of description. I won't go into it, but this is one way of doing it, and this is why this whole thing works. Right? We observed that the dimension of the space of our signals is finite. Once you fix the set F, we have a finite dimensional vector space. Right? Which means that if we have a Krylov subset, right? Vectors x, bx, and the powers. Once we go beyond the dimension, one more than the dimension of that finite vector space, that system of vectors is linearly dependent. And therefore, we can find a non-trivial linear combination, which is 0. Right? And the coefficients in that nonlinear combination form the coefficients of the Prony's polynomial. And the roots of these polynomials are precisely, all of them will be in F. This is one way of doing Prony's method. You form a sequence of linear equations, well, system of linear equations, not even a sequence, it's finite. You find the coefficients of Prony's polynomials, the zeros are the roots are in the spectrum. So in all of the specific cases, you just need to make sure that you captured all of the roots, that you don't have them collapse into one, that your function h is actually 1-to-1. So there are details to get through, but this is the crux of the method, right? You form a linear system, and the solution, the specific solution with the first coefficient being 1, and as many zeros here as you can possibly have, well, those coefficients give you the coefficients of the Prony's polynomial. The roots are in your spectrum. And if you're lucky, you've recovered all of the spectrum this way. So this is the outline of the algorithm. Your goal, again, is to find all elements x of that form, the linear combination of eigenvectors and generalized eigenvectors of the representation from the measurements by A, B, from the dynamical samples, essentially. A, B, B to the Lx. Right? So you input those measurements, you choose the function h that works, needs to have some mild conditions, should be 1-to-1. Take the desired number of measurements, set up the linear system, find the coefficients. Those coefficients form Prony's polynomial, find a set of roots, and then if all the conditions hold, you apply H inverse to that set of roots. Remember, H is 1-to-1, and you recover your spectrum F. Once your spectrum F is known, your measurements become linear, so you just solve a linear system to find the coefficients, and that completely recovers your signal X, provided that, again, your system has only one solution. So these are certain assumptions you need to make on the operator A. And in certain cases, you can prove that you have unique solutions. In other cases, well, you get all possible signals that satisfy your measurements. And notice that this is one way of describing the classical Prony's algorithm as well. It just happens to work in a much, much more general setting. So now let's go back to the few examples that we started with and see how it works there. I decided to go a little bit more generally than the original Prony's method. So rather than look at almost periodic function, I look at the combination of exponentials with polynomial coefficients. So my Q gammas here are non-zero polynomials of a given degree. Right, so it's a slightly more general problem. I'm not sure if it had been considered before. My apologies, I forgot to check the literature on that. But anyway, so you have to be a little careful which space you're working with, and it turns out that this is the space you want to look at. You want to look at bounded uniformly continuous functions, but also they should stay bounded uniformly continuous when you divide by 1 plus x, absolute value of x, quantity to the m. Right, where m is precisely the highest degree there, the highest degree of the polynomial. So this is where you need to go to spectral submodules, which are not one-dimensional. They'll be m-dimensional. And this is also the case why you need Berling algebras, because the translation on this space is not bounded anymore. It's grown, but it's grown polynomially, so it's all good. Right, the module structure is convolution, as we discussed before. And then you get the theorem, which is a straight generalization of Crony's result, or a straight generalization of basic super resolution. So you have a sort of enormous periodic function, but the coefficients are now polynomials. Each coefficient is non-zero, has degree at most m. The spectrum is a finite subset of a half-open interval. You can scale it, but for simplicity, just the half-open interval. This is the number of measurements that you need to take. So you take x of 0, x of 1, and x up to this number, consecutive measurements. And then the algorithm from the previous page allows you to completely recover this polynomial here. And there is a little bit of non-triviality to show why when you do the measurements, that gives you that operator A. So it requires a proof why the system for coefficients of these polynomials has a unique solution. So it's a linear system. You need to show that the determinant of that is non-zero. And that's a little bit of computation by induction, which is tedious, but it works. I was trying to get it from different, more abstract reasons, but in the end, Götz and I just ended up computing the determinant. As much as we wanted to avoid that, we couldn't. So if anyone could give me abstract reasons for not doing that, that would be helpful. But anyway, so this is one of the easy generalizations of Prony that you can get from the abstract thing. Here is a slightly different problem related to dynamical sampling, not the one that I mentioned before. So it's called a sparse dynamical sampling. And what I want to do here is closer to the original problem, but which is identifying the initial condition of the initial value problem. Right, so A here is the generator of a group, or a generator, which is essentially a generator of a Banach module. And we don't know the spectrum, or we don't know which part of the spectrum is there. So X naught itself is of the form of our signal, which means that it belongs to the spectral submodule of the module generated by the operator A. And then the measurements are here, again, the dynamical samples. And this problem fits the general framework with this group. Right? Now I'm cheating a little bit because the spectral mapping theorem that I showed you doesn't work here. This representation could grow too fast in general, but there is a different spectral mapping theorem which will work in this framework as well. All right, so again, the measurements are this. Right? You are looking at equally spaced values of the solution of your differential equation. You're measuring them against an orthonormal basis of your space. And then you use the abstract method to find the spectrum, which in this case is F, right? So this is part of the spectrum sigma A, where the X naught really lives. So this is an example of how that general point of view applies in the case of dynamical sampling. And again, Prony's method is a special case of this. Well, finally, we're getting close to the end. I have only a few minutes, so let's take a quick look at the channel identification. The problem here is to identify the operator, finite linear combination of time frequency shifts. I'm making an assumption that the spectrum is part of the square 0, 1. I could choose any compact I wanted. I need to identify the group. Well, the group is R2, so the dual is again R2. I have to make a choice of my characters, and the usual time frequency choice is this one. So this is how R2x and another R2 to provide this duality. Right? This is the representation of the group, which is the conjugation by the time frequency shifts. The interesting part here is that if you look at pi g itself, just this, they won't form an abelian group. Right? It's the Heisenberg group that's behind. That's, of course, isn't abelian. But when you do the conjugation, those unimodular factors cancel each other, and suddenly this conjugation does define a representation of the abelian group R2. And then the time frequency shift by gamma corresponds to the, it actually is an eigenvector of this representation that corresponds to the eigenvalue gamma of g, where gamma of g is given by the formula here. So now we can completely set up the structure, right? We just need to explain the measurements. Well, here are the measurements. I'm choosing the Gaussian. I'm choosing finitely many time frequency shifts of the Gaussian, and I'm applying x to this finitely many time frequencies. So it's essentially frame coefficients in a way. And I believe these measurements are the ones that Charlie used in the paper with his colleague that I cited a little bit earlier. Another slightly non-trivial thing here is to find a function h that satisfies the conditions, so which is in particular 1-to-1. Right, so of course the naive thing would be to just do t of 1, 1 or t of 1, 0 and t of 0, 1, something like that. Turns out that you can't get what you want with the naive thing, but you can choose this function h. You can prove that it's actually 1-to-1. So this is the inverse. You can explicitly compute it. You get this funny formula, and then the algorithm works. So you do the measurements. You have the operator b based on this function h. Then you compute a applied to b to the power l x, where ax is this. These measurements really are a finite linear combination of pretty much things like this, but you'll have other entries here. So you are really getting the measurements of the type that Charlie was using in his paper. And then you apply the abstract method. As a result, you get back the time frequency shift, the combination of time frequency shift encoded by the operator x here. And with that, I thank you.